Good morning, sir.
Good morning, sir.
Okay.
Good
So
morning,
welcome
sir.
back. I'll start the session now.
Yes, sir. Just a minute.
Okay, sir.
Hi, sir.
Good morning, one and all present here. So it gives me an immense pleasure to welcome you all to this online workshop on Qiskit and Quirk. In today's rapidly advancing academic and research environment, tools like quantum computing are no longer optional. So they are essential. That's what today we have organized this one of these workshop on Qiskit and Quirk for the VTU faculties. I would like to I would like to introduce the speaker, Dr. H. Ashwathaman. Doctor is a professor from NPS Saptagiri University, Bangalore. So he has over 17 years of teaching experience. He has begun his doctoral research in 2011 at Alagappa University, Karaikudi, Tamil Nadu. His research interests include natural-based energy materials and electrochemical studies, as well as quantum computing. He is actively associated with Center for Quantum Computing and the Energy Research Laboratory, contributing to interdisciplinary advancements in physics and emerging technologies. So, with this, I would like to welcome resource person plus. Okay,
Yes.
please
Good
take over,
morning,
sir.
everyone. Yeah, good morning, everyone. Can you hear me?
Yeah, you are audible, sir.
So I'll share my screen. My screen is visible.
Yes, sir. Yes.
Hello. Hello.
Yes, sir. It's visible,
Ah,
sir.
okay, okay. Here. Okay. So today I assume that the participants know about quantum computing. So I no need to give the background about quantum computing and all. I assume that they know about gates and they know fundamentals about quantum computing. So how to implement it? That is our focus. Is it okay, sir?
Yes, sir. Yes, sir. Please proceed.
Okay, okay, okay. So this session we'll have how to implement quantum circuits in different platforms. So we are going to use Quirk and IBM, and also I will show you how to run a program, type a program in using Python and run it in Google Colab. So we can use different platforms. So these three platforms I am going to explain. So the important thing is in the VTU syllabus it is given single qubit gate and the multiple qubit gates you have to implement and show to the students. So that will be our main focus. For that we can start with gate. That is the important thing is Bell states. So Bell states is the entangled states. So we have four Bell states. So I can write like this. So I will show you what are Bell states, and I'll show you the product states which are not Bell states, which are not entangled. So this one is correlated. This is one bell state. This is another bell state. So all these states are entangled. So to understand this, I'll write a product state. So let it be like this: 0 plus 0 0 by root 2. See, if you compare these things, no, this also looks similar. So this looks similar to bell states, but this is not a entangled state. It is just a product state. So I can write this, I can split and write it as a two components which you multiply, you'll get this one. So I'll write this as ket 0 plus, sorry, ket 1 is ket 1 plus ket 0 divided by root of 2 multiplied by 0. So now if you multiply it, what you get is, you can multiply and write it 1 0, you'll get plus 0 0. So this state, what I have shown, is a product state, and this is not entangled. You cannot write this bell state like a product state. So you can try to write this whatever is given here. Try to write it as a product of two things. That is, if you multiply two components, you have to get this one. You will not be able to write it. So it is a entangled state. So what is this entangled state is, if you measure it, you will get any one option, that is 0 0 or 1 1. So 1 qubit is 0 means we'll come to know that the other qubit is also 0. So that is why it is entangled. If 1 qubit is 1, we'll know that if you measure 1 qubit as 1 and other qubit will be 1. So that is what correlation, and this is positive correlation. 0 means 0. Here you see that if you measure this, two possibilities are there: 0 1 1 0. So in one place, if you measure 1 qubit as 0, the other qubit should be 1. If you measure 1 qubit as 1, the other qubit should be 0. So this is also entangled. So in this case, we cannot do like that. So if you get 1 0 0 0, so if you get 1 qubit as 1, you cannot say it is 0 or 1. So that is why it is not entangled, it is a product state. So this is all about bell states. Now we will see how to construct a circuit. Okay. Otherwise, is there any other? We'll see how to construct a circuit for this bell state. Okay. So the bell state is, we are going to take this state. Just it is a naming. So how to get this state? So by experience, you can get it, how to use this state. So 1 by root 2, you have ket plus another ket. So this we can get it from a Hadamard gate. So this kind of structure, you can get it from Hadamard gate. So I'm going to use a Hadamard gate, and I'm going to give a input as ket 0. So you all know that the output for this Hadamard gate will be 0 plus 1 by root 2. Now, it is single qubit gate. This one is single qubit gate. What I showed is single qubit gate. But here, this is 2 qubit gate. So I want to explain you this representation is a simplified notation. So actually this is get 0 multiplication by get 0. This multiplication is called as tensor product. So usually the product, two types of products are there. One is inner product and another one is outer product. So these two kinds of product we can take, and this will give a scalar. It's a scalar product. This will give a matrix. So this is how we will use the product. So in this case, always we have a product of a space. This kit 0 is a space, and bra 0 is the dual space. So we will always take the product between a ket and its dual. So always we have to take a product between ket and bra only. So you cannot take product between two kets. So if you take a product between two kets, that product is called as tensor product. So what will happen in this tensor product is you all know that how to represent this 0. 1 tensor 1 0. So this tensor product, every point you have to take a product. The first product will be like this. The output will be 1 into 1, 1, 1 into 0, 0. Next, you have to take this component with other components. So 0 into 1, 0, 0 into 0, 0. So this product is called as tensor product. So what is happening here is, if I write get 0, I can write it as 1, 0. 1, 0 means it is a two-dimensional vector. 2D vector. Here you see that when you take a tensor product, you get four-dimensional vector. So when you do tensor product, your dimension is increased. Okay, so this one, what we are writing, this can be written as 0 tensor 0 ket, or you can write it as 0 0. So everybody should understand that if we write 0 0 means it is nothing but tensor product between two vectors. Okay, if I write 0 1 means it is a tensor product of 0 with 1. So this is what in the simplified manner we write like this. So the 0 0 means it is tensor product. So tensor here you have two qubits, 0 0 2 qubits, but we are getting only one qubit. So we have to multiply with another qubit. So one possibility is I can multiply with 0 or 1. So I'm going to use two qubits here. So I'm going to give another qubit. So whenever we have two qubits, then we have to take tensor product. Okay. So what happens is this 0 we have to take with the tensor product get 0. So tensor product, each and every component we have to multiply. So 0 with the 0, we'll get this one plus 1 0 by root 2. So we get this. The output here is this one. So when you have a Hadamard gate and another qubit 0, if you do it, so you'll get 0 0 plus 1 0 by root 2. But you see our Bell state is different. First component is okay 0 0. Second component is 1 0. So to convert this, what we can do is we can use we have to convert this as 1. But you can apply for both the states. Okay, you cannot do it only for one state. So we have to apply a gate which will not alter this one, but which will convert this into 1 1. So what is the gate is we can use, and 2 qubit gate is there. So we can use 2 qubit gate. So that qubit gate is 2 qubit gate is control not gate. So we can have a control here and control not gate. So now what happens, you see, control not gate operations, you know, this is the control, this is the target. When control is 0, the target will not be affected. So this is the control and this is the target. So when control is 0, the target will not be changed. So it is 0 0. plus when the control is 1, the target will be flipped. That is what control NOT gate. So the target is 1. Now the control is flipped. It becomes 1 by root 2. So we got this one. So the simple circuit is we have a 2 qubit gates. One is Hadamard gate, that is a single qubit gate, and another one is C0 gate. So Hadamard gate followed by C0 gate, the output will be your Bell state. So similarly for all the Bell states, we can do it. So you can try for this one. Just we'll give an idea for this state. So what to do? How to construct the circuit? So it's very simple. We have to start with negative sign here. So negative sign means we have to start with qubit 1 to the Hadamard gate, and you will get 0 minus 1 by root 2, and we have to multiply with 0. So I'm going to have one more qubit, that is 0. Then I will have a C0 gate. Then you will get this result. So when you get C0 gate, you will get 0, 0 minus 1, 1 by root 2. So we can design the circuit depending upon our formula. So we can design our circuit and we can implement it. So there is another circuit. This is not only the case. We have another circuit where we can have superposition entangled state. Okay, so this circuit, just I will draw it and we'll analyze it. So this will help you how to analyze any circuit. So I have two Hadamard gates, and this is also a entangled state. You cannot write it as a product state. And I have a control Z gate. So this is one circuit where this will also create Bell states. Okay. So we will have an input as get 0, and in quantum circuit usually we will stage by stage we will check what is the output. So that is what I am drawing the line. So here I can give it as psi 0, here it will be psi 1, here it will be psi 2. That means what is the output at this stage. Okay, so first psi naught. What is psi naught? So it is nothing but two inputs are there. So whenever you have two gates, it should be a tensor product. So psi naught will be get 0 tensor product. The symbol is tensor product. Get 0. So you will get 1, 0, 0, 0. So then what is psi 1? Psi 1 is nothing but Hadamard gate, another Hadamard gate. So tensor product between Hadamard gate into Hadamard gate. What is the input? Input is 0. So the Hadamard gate input is 0. The output psi 2 will be a tensor product of Hadamard gates with input 0, 0. If you put it as 1, it will be tensor product of Hadamard gate with 0 and tensor product of Hadamard gate with 1. So Hadamard gate outputs we already know for 0, that is 0 plus 1 divided by root 2 tensor product. Again, the output of Hadamard gate for 0 is root 2. So what will happen when we do the product? We have to do each and every component. So first I will take this 0 and multiply with 0 and 1. So I will get two components. Okay. So what I get, I'll have this 1 by root 2 into 1 by root 2. It will be 1 by 2. For every product, it will be 1 by 2, 1 by root 2 into 1 by root 2, 1 by 2. So 0 into 0, it will be 0, 0, plus 1 into 0, 1, 0. Then plus, we have to multiply this with this one and each one. So it will be 0, 1 plus 1, 1. So this will be the output at psi 1. Next, what we have control Z gate. Control Z gate. So as we have discussed earlier, so the first qubit is control, the second qubit is target. For each and every case, it is like that. So what is the Z gate operation? Z gate, you know what is the Z gate operation? If it is 0 means nothing will happen. Whenever the control is 0, you will get the output same. Second target qubit will be same. If the control is 1 and if it operates on 0, if the control is 1 and if it operates on 0, there will be, just a minute. The control is 0, there will be no change. Okay, if the control is 1, if it acts on 1, it will inverse the sign, negative sign will be there. So that is the Z gate operation. I hope everybody know it. I'm not going detail into Z gate. Okay, so now we can see that what will be the output at psi 3. So the psi 3 will be equal to, you have 1 by 2 and the control is 0. So there is nothing, no change in the target, plus the control is 1 and 0 is there, so there is no change. Again we get 1, 0, plus control is 0, target no change, 0, 1. Now control is 1, the target is 1, so it will flip the sign. So what happens is it will become minus 1, 1. So this state is also a entangled state. So not only Bell state, so you can have different entangled states. So this state is also a entangled state where the probability will be 1 by 4 for each state. Each state the probability will be 1 by 4. Okay. So this is an example. So how we can analyze a quantum circuit step by step. Okay. So now, is it clear? Any doubt?
No, sir. Please proceed.
Okay, so now we will move on to the platforms where we can implement these gates and see how to operate it. Okay.
Sir, here you please show them where to log in and how to start proceed with it.
Yes, sir. I'm just showing from the beginning, sir. Okay, first, we'll see this Quark software. Just type this one. You'll get Quark simulator. So you can Google search because already I used it. So you'll get this one. You just type it. You'll get this Quark simulator. So in this, we have tutorials are there. So you can see the video tutorials, how to use this. You can go through this and how to use the software. Okay. Just a minute. So so many things are available. So you can do this. And you have source code is available and how to use it manual is also there. So you can see the manual how to use this software. So all these things are given here. So now we'll see, we'll run our circuit and check how it is working. And you have already circuits are there. So Shor's algorithm, Grover's algorithm, Bell inequality test, all the circuits are there. Just I'll type this. So this is the algorithm. So what we have shown is a very simple circuit, and this circuit we have Hadamard gates. So because you can see here, this gate is a X gate, we need input to the Hadamard gate as 1. So we have always the default input is get 0. So when we put X gate here, the input to the Hadamard gate is 1. So that is what. So you have so many, it's a very big circuit. So you have to analyze each and everything. So, but we are not going to do this now. You can just uh, do it. So now we'll come to this Quark window. So here you have important things. What we have to take is gates. So this is a Z gate, Y gate, and X gate. So these are all single qubit gates. And then you have uh, Hadamard gate. Hadamard gate is here. So Hadamard gate is here. S gate is here, which rotation and descriptions are given here. You can see the descriptions, and T gate and inverse of S gate. All these gates are, Z gate is there. So you have all the gates, and we will use mostly these things only for our things. And these are the displays. Okay, so this is Blot sphere, and you can have amplitudes, and on off is the binary thing. If it is off means logically it is 0, that is get 0, the measurement is 0. And if it is on means it is get 1, logically it is 1. So that is on off, one type of measurement. And this is Blot sphere measurement. So you know that when it is pointing upwards, it is get 0. So that is why the it is vector is pointing upward, and here also vector is pointing upward. And then these are the amplitudes. What is the amplitude of 0? Amplitude is maximum. So these are the amplitudes. So different displays are there, and you have controls and all is there, X gate, Y gate controls. And these are all little bit complicated one. When you use different circuits, you can use this. So for our purpose, we'll use these things only, and very few gates and display. Okay, and this is very easy. We can click and drag it. So that's what we can do. And here what you are seeing is 2 qubits are available now. So if you want to increase the qubit, you can increase the qubit, just click someone, then the option is giving another third qubit. If you place it there, then you will get the third qubit. Similarly, if you want 4 qubits, you can use it. This is just a simulator. Okay. So very simple thing. First thing, we'll see how the X gate works. So I take X gate. See, now before that you can see there it is off, and the vector is pointing upwards, that is 0. Okay, so the input is 0. So the input is this one. So when I put the input is 1, it becomes on. I can change the input here. So it is on and it is flipped down. Okay, so now I'll have 0. So I'm going to use the X gate, and I'm going to drop it here. That's all. It's drag and drop, very simple. So now you see that the input is 0, the output is on. That means 1. So it works as a X gate. So you know that all the gates are, if you use 2 times, you will get the same. So now you will get the output as 0. So this is how we do it, and just click and bring it back. You can remove the gate. So this is easily you can do it. Okay. Next thing is I am going to construct a gate, control X gate. This is control. Just a minute. Control X gate. X control. I'm going to keep control here. And yeah, some problem is happening here. No, not this one. We can use this X gate here. Now it is control X gate. So you can see that when control is 0, and we measure both the outputs in the 2-qubit gate. This is A when control is 0, and there will be no change in the control bit. So whatever control bit is there, that will be there, and the control is off, so there is no change in the target. So if I change the control as 1, so what happens is whatever control is there, same thing. So I change it. Yeah. So now whatever control is there, same thing you are getting as an output. So there will be no change. When control is on, the target is flipped. So it is flipped from 0 to 1, and this can be shown here. Okay. So this is how you can implement different gates, and you can show it here. So if I put Hadamard gate, what will happen? You can see the Hadamard is a single qubit gate. So if I use Hadamard gate, what happens? You can see that this blot sphere, the Hadamard gate will create a superposition principle. So that means this vector will be exactly in the middle and pointing positive x direction, positive direction. So I put Hadamard gate, so 50 percentage. So that is 0 50 percentage and 1 50 percentage, and you can see that it is in the forward direction. Okay, so if it is 1 means it is 0 0 minus 1, so then this will point backside, so it is pointing about backside, that is minus 1. So this is what you have Hadamard gate. Here you can see this amplitudes. Okay, what is the direction? Okay, so these are the things what you can show it here, and here we can see the show the Bell states. So you know that Hadamard gate followed by a C naught gate. Hadamard gate followed by C naught gate. So I have a control here, and I have a X gate, CX gate. So this is the Bell state. So the output is 50 percentage. You know that output, Bell state output, you know. So this yeah, this one 0 0 is having a 50 percentage, and 1 1 is having 50 percentage. So that is what we are getting it here. So 0 0 0 50 percentage, 150 percentage, 0 50 percentage, 150 percentage. So that is what entangled the state. And similarly, if you want to change it as 1, then also you'll get 50 percentage, but it is negative. So using this, you can check this, what is this negative. So now I want to know each and every step, what is the output. Okay, so for that we can bring it and put in between this one. So now you see that, and I want to know what is the input here. So see, the input is 1, so the vector is pointing downwards, and when it goes to Hadamard gate, it is pointing backwards, and when it passes through this C naught gate, it becomes in the middle, that is 50 percentage both. So both are entangled. So if I want to change this around, you can show to the students. And this one, so now the input is 0, it is shown here. After Hadamard, it is that, and then we get C naught gate. So this is how we will we can use this, and you can store and you can take printout, all these things we can do and maintain it for this one. So by using continuously, if you use, you can learn this one easily. So next platform what we are going to see is we are going to use IBM. So you just type IBM quantum experience, so you'll get IBM quantum platform. So this is the window, and it is also similar. You can have documentation, tutorial, all these things are there. In this, what we will use Circuit Composer. So this is second experiment. One you can use Quirk, and another one same IBM you can use it. Okay, so here it is a simulator. If you want to work on real quantum computers, that is, you can construct a circuit and you can run it on a quantum computer. So for that you have to use Qiskit, and you have to have a login, and you have to pay for it whenever you run. Previously it was free. Some hardware was free, and you can run the circuit whatever you have. But now they made it as chargeable, and that two types of memberships are there. One is a ordinary membership, another one is premium membership. What is the difference is number of qubits. Okay, so whatever you want you can do in the same thing, you can get it here using IBM quantum platform. But what is the restriction is you can use only 4 qubits. The maximum qubits allowed is only 4 qubits. If your circuit is within 4 qubits, you can construct here and you can run it. If it is going more than 4 qubits, you cannot do the simulator. You have to log in and pay the amount, and you have to do it. Okay, and this you have more visualization, same visualization, but here it's not a block sphere, it is a state vector. Here you can have only state vector. There is a difference between block sphere and state vector. Here the state vector will be 2-dimensional only. There you'll get 3-dimensional. Here it is 2-dimensional. Okay, so all the gates are there. You have Hadamard gate, you have NOT gate, C NOT gate, and Toffoli gate, that is control NOT gate, swap gate, I, T, S, Z, all the gates are there. And this one is for measure. So wherever you want to measure it, you can measure this one. And this is barrier to segregate the circuit. It's just when you visualize the circuit, you can say it will not do anything to the output or anything, but it is a barrier control, and all other rotation gates are there. RX, RY, RZ, all these gates are there. And so this we can control it, we can do it. And if you don't want, I'm going to use, and what is the thing is, if you have 4 qubits, and here you can see that the output and the output of all 4 qubits will be there. You can see 0, 0, 0 is there. And if I don't want, I'm going to use only 2 qubits, means I can delete this one. So if I delete, it will become 3. So I'm going to use only 2 qubits, means I can delete, and it will be 1, and delete, it will be 1. So 1 qubit, you have only 2 states, 2 possible states are there, 0 and 1. Okay, so we'll see now what is the, and here always the default qubit is 0. So I want to see, I want to change it, means I have to put a NOT gate in front of this. That's what we have seen in the circuit, Shor's algorithm. So now what happens is the input is 0 and I have a NOT gate, the output is 1. So we are getting this output as 1. So this is the one visualization, and you can have a table view also. In the table view, you can see that amplitude is 1 for 1. If I remove this one, you can see that 0, the amplitude is 1 for 0, the output is 0. So these are the two views what you can have. And here you have Q sphere and the probabilities. So two options are there. Probability is what we have seen, and here also you have table view. But when you use Z gate and all, it will be very much useful. I will show you what are the how it is operating. And Q sphere will give the sphere, and here phase angle is there. But now we are not using phase gates, so there is no change. So always phase will be 0. And here you see that as I am having only one qubit, so this multiple qubit gates are disabled. So now you can see only one qubit gates are available to click and drag in the equation. And this is the code automatically it is generating. So you can also uh, add code here, that also you can do. Or if you see, for example, I am going to q1, only one qubit is there, so that is why it is q0, first qubit, and c4 is the classical output measurement. So C4 is there. Okay, so these are the two things. When I put Hadamard gate, you can see that the code will change automatically. When I put Hadamard gate here, so I'm adding Hadamard gate, so it is coming here. So now you see that the amplitude becomes 0.707. So for 1, it is 0.707. For 0, it is 0.707. 0.707 means 1 by root 2. So 1 by root 2 into 1 plus 1 by root 2 into 0. So that is the output of Hadamard gate, you all know. So that is the one. The graphical view, you can see that this gives the probability. So the equal probability for both 0 and 1. So it is in the superposition state. And here you see that both the vectors are available here. But in the blot sphere, in the Quirk, we have seen that it has shown in the forward direction. So whenever I have Hadamard gate, you see that it is showing in the middle. But here in IBM, it will not show in the middle because it is two-dimensional. Okay, and the phase angle, if I include phase angle, there is no change in the phase. So this is how you can use, you can show Hadamard gate. So now I need one more qubit. I want to add it. So just click here, and plus means you will add one more qubit. Okay. So here important thing is the lowest digit will be the one. The first qubit Q0 will be the right hand side. Okay, 1 0. Here it is 1 0. The output is for example, wait just a minute. So 0 0. That means first one is 0, second one is 0. If I put a NOT gate here, so it becomes 1 0. So you have to read from the right to left. So first qubit is 1, second qubit is 0. So that is how you have to learn. You have to read. If I include another qubit, it will be 0, sorry, 1. This output is 1, 1 here, and next one is 0, 0. So if I put here another not get here, what will happen is it becomes 1 1 0. So you have to read it from this side, 1 1 0. Okay, so this notation we are going to follow it, and we will go to our circuit. So where we can show that we have a Hadamard gate followed by C naught gate. So now this is the Bell state, and it is just a representation. It's qubit 0, qubit 1, like that. It doesn't mean that it is 1 or 0. Always the input will be 0, get 0 only. So it is default. If you want to change, you have to add a not gate here in front of this X gate here. Then it will change. So now you see the output. The output is equally 0 0. That is 0.707. So that is 1 by root 2 0 0 plus 1 by root 2 0 0. And even in the this also you have equal probability, and this is what your Bell state. So if you want to have If you put 1 here, so it becomes red color. So what does this red color represents? So 0, 0, the phase angle is here. You can see that the color code is here. I think you can see it here. 0, the phase is 0. Red means 180 degree. So 180 degree means exactly opposite. That is minus 1, 1. Okay. So that is what this red color shows. So phase angle is 5, 180 degree. So minus side. This side is positive and this side is negative. So it is negative means minus 1, 1. So 0, 0, 1 by root 2 minus 1, 1, 1 by root 2. So that is what we are having it here. And this circuit, what I've shown is I kept it this one. So this is the output. So all these things you can explain to the students. And you can explore it, even Z gate, all these gates. So Z gate, we'll see. Okay, one more thing. And how it works, to show it to the students, we have this inspect is there. Inspect. And stage by stage, you can see what is the output and what is the input. Okay. So inspect. Okay. So now Hadamard gate. See, first the input is 1, 1. And next the Hadamard gate 1, 0, 0, 0. So this is the output of Hadamard gate. And next, if I click this one, it will show the output after this stage. So it becomes 1, 1. So you can show that how each step is changing in this IBM quantum experience. Okay. So the next what we will see is we will use
So should we measure that using classical gate, sir?
no, sir. Automatically it is there. If you want in between that, you can use this measure symbol, and you can do it. See, automatically at the end it will be measured, sir. Whenever you construct a circuit, it will measure here and it will give the output. In between that, if you want to measure, then you can use this measure symbol. Wherever you want, you can measure it, sir. That's you can do it. See, I want to measure it here means I can get the measurement here. What is the value? So like that you can do. Wherever you want, you can measure it, sir, and you will get the output. Okay, sir.
Okay, sir. In the Q
But
sphere,
this
yeah.
measurement, what will happen is it will not disturb the circuit. That is the one.
No,
When
here
you measure
in Q sphere, sir, after measurement it is showing only after Hadamard
one
gate it
one,
should be 50-50, right?
yes, sir. Adamad gate one. This is once you measure, it will collapse, no, sir. That
Uh-huh.
is what it is showing.
Okay.
So whenever you measure it, your say Adamad gate output will be uh, one plus ket 0 plus ket 1 by root 2.
Mm.
That is before measurement. When you measure, what happens? It will collapse to any one state. So it is collapsing it to one state. That's what. Now the
So,
probability is 0.
so either it collapses to 0 or it collapses to 1, right?
Yes, collapse to 1. Yes, sir.
So now to see that for the next trial repetition.
Next trial, we'll see what happens. Again, I'm going to take this 0. Again, 0 only. So it depends upon the timing. It's 0 only, it is coming always. We have to measure so many times.
Got it, sir. Got it. Thank you.
Yes, okay. That's what, sir. If you measure means it is collapsing.
Mm.
So shall I move on to next one?
Yeah, please, sir. Please.
Okay. So Z gate, see, for another thing is what I have shown it in the this one itself. Z gate, if I use Z gate here, So you can see it as 0 0, and if I change it as the input as 1, this is how we can change the input as 1. So it is 1 and the color is changing. The color is changing means the phase is changing. So here, what is the color? Depending upon that, you can check the phase. So it is pi, 0 degree and pi degree. Also, how to measure with the color means instead of that, you can go to the table view. And that's what I said. I'm having only one qubit gate. So it is a little bit confusing. So I will remove one qubit. So we'll have only one qubit. So now you can see that 0 is not there. Amplitude, the output is not 0. Output is 1, and it is pi. Pi means the direction is negative, so it is -1. So that is how this phase is measured for rotation gates, and the color also changes. In this graphical view, you see that based on the color, you can check it. Okay, so instead of Z gate, if I use S gate, so now purple color, so it comes somewhat here. So I don't know how to measure it, so I can go here and table view, it becomes pi by 2. So it is pi by 2 here. So that's how you can measure the angle, phase angle. I think you can explore it so much, so many things are there. You can keep on explore it and do it. Okay, so I'll move on to the next one. That is, we can go to Google Colab. So I will use new one. So I already shared the Bell State codes. I'll discuss the code. So this is, you can copy it from the notepad and you can paste it here. And if you run, you will get a error message. Just like, just it's Google Colab. You can open it and you can run. So what I'm getting is, I'm getting some error. So why this error is happening is, so this Colab, we didn't install Qiskit. So before running this, every time we have to install Qiskit. So that I will show you how to do it. So just type here code. So I'm going to install this one, space with install Qiskit. So you have to type this one and run it. Every time, whenever you run, you have to do this one. So now it is successfully installed. Qiskit is installed. And what is the simulator we are going to use? So we are going to use Qiskit Air. So that also we have to install it. Air, and run the program. Okay, spelling mistake. So it's easy. You can, it will give what is the mistake we are making. We can go through it and we can run it. So successfully installed. So now you see that the error what we have is, we are having the program, but import required libraries. So that libraries only, we have it in Qiskit. So that is why now we installed Qiskit. And then now if we import, we'll get all these things. Now I will copy this this code, so it is already written, and after running this, I will paste it. So here we'll discuss about the code. What we are going to have in this code is, we have Qiskit in that quantum circuit and transpile we are having it. So why we are using transpile is, all the hardwares will not have all the uh, gates. It is not possible. So whatever gates we study, it will not be available in the hardware. So whenever we make a circuit, and depending upon the hardware, the circuit will change with the available gates. So whatever operations you want to do, it will change with the available gates. That's what we need transpile. And then here is the simulator what we are using. Qiskit here is the simulator. And then visualizing tool we have, and the plotting tool we have. So these are all the things what we have in this libraries. And then this is the circuit. So quantum circuit, 2 by 2. So we have 2 qubits. That's what 2. If you want to 3 qubits means you have to do 3. And the measurement on the both the 2 qubits we are going to measure. So that is why whenever measure means it is classical. So 2 by 2 means 2 qubits and 2 classical measurements. And then we have a quantum circuit, Hadamard gate, which is at Q0. First qubit, we have Hadamard gate. And from the quantum circuit, we have CX gate, control X gate. So it is first qubit is 0, that is control, and second qubit is target. So if you want, you can also add CC not gate, but here it should be 3 by 3 because it is 3 qubit gates. So quantum circuit 3 by 3, and we are going to measure all the 3 outputs. 3 by 3 will be there, and you can add CC X 0 0 1. So then it will be control not gate. So you can do that, and measurement we are going to do on both the qubits. So that is why 0 1 0 1. Okay, 3 qubit means 0 1 2, like that it will be there. And next, this is what construction of the circuit. So I think it's very simple. And I will tell you, I'm not from what is it, uh, programming, from this programming. I'm not there. Whatever required for quantum computing, I'm going from this side. Whatever is required, I'm learning in that way. So I'm not masterizing the program and coming and doing program for quantum computers. Okay, Qiskit, I'm not doing it. Whatever is required, I will do, and I'm learning. That way only I'm doing. Okay. So next is run simulator. So we can run this air simulator. Simulator is air simulator, that is equal to compiler circuit is transpiler QC sim. This is the compiler circuit, and then transpiler is the compiler circuit. Result will be in simulator.run, and here quantum circuit, and we have shots 1224 shots, and result is 1. So what does this shot means me? This circuit we are going to run it for 1224 times. So that is what it is given here shot, and then count the result. For each count, what is the output, we'll count and get that count. So this is the run, so running the circuit. And then all these things are all whatever you want, you can show it as output. So here I'm going to give the circuit, draw circuit. So whatever circuit we have given in the code, it will be drawn. So we will visualize it. If you don't give this one, circuit will not be visible. So that is what draw circuit. And then histogram. So measure the results, and it will give how many counts are there. Print count will give how many counts. And then next I want to show it as a bar chart. So I am using all these things, bar chart, everything I'm giving. So this is the bar. Okay. So now this 1000, yeah, 1024, it will be 512 512. It will have the same value. So now we'll see, we'll run and see it, what is the output. So I'm going to run this one. So it is over. So executed in 0.99 seconds. It's very simple circuit. So you can see that first we have print counts. So that count is here. So 1 is 494. That is get 1 is 494 times. Get 00 is 530 times. So Here it is almost equal. So one can ask a question. It is a simulator should give equal part, okay? But this now the Qiskit is made it like whenever you run it in a real quantum hardware, how you get in the same way, this will give the result. Usually one time if you run itself, it is enough in a simulator. But to make us to feel how it will, you will get the result in the real quantum computer, that way it is designed now, okay? So this is what you have, and this is the circuit what we have done. So a Hadamard gate followed by control X gate. Measurement is done in both the qubits. That is what 2 by 2. So that is what 2 by 2. And then this is the bar chart. You can see that 1 1 is some 400 something time, and 0 0 is this one. So even it is a simulator, it gives the feeling of running in a real computer. So one can note down this 494. So again I am going to run this one. The second time I am running, it was 494. Now it is, see, now it is changed. This becomes 494. This becomes 530. So same thing only, I think. Only this is changed. Again we will run and see what happens. Yeah, 492, 532. So like that. Whenever we run, it is giving a real experience. Okay, similar to the real experience. So this is how we run it, and you know that equal probability 1 by root 2 into 525 00 plus 1 1 into 525 plus 00 into 499. So times, that is what given here. So this creates a Bell state. So this is what we have shown it here. And if I change it as only one time, I'm going to run it only one time, shots. So what will happen here? You see that result, we are getting 5 to 5. It will be only one. So you will get either result 1 1 or 0 0. Any one only you will get it. So I'm just running it. See, count 1 1 is not coming. 100 percentage 0 0 is the result. If I run it for 2 times, shot, that's number of shots. If I run it for 2 times, so 4 possibilities are there. I can get 0 0, or 1 time 0 0, 1 time 1 1, 3 possibilities, or 1 1. So we'll see that. We'll run and see what are the output we are getting. So 2 times also 1 1 only we are getting. So again if I run, so 2 times I am getting 0 0. So we'll have some 10 times. See now, 10 times, 8 times I am getting 0 0, 11 times I am getting 2. So this is how, when you run it really in a quantum computer, you will get like this. So this is what you call it as error. So a separate field is there, quantum error correction. So after a circuit, you have to do it. Okay. So with this, I'll stop here. If you have any doubt, you can, we'll have a
So
doubt.
in place of Bell state, if you use Hadamard gate also, you'll get same result, right?
Sir, where, sir?
Here in Bell state, you have used H gate with NOT gate.
Yes, sir.
So if you use
Yes, sir.
Hadamard gate also, 50% you're supposed to get.
That is, you'll get only single qubit, sir. That one.
Yeah.
You will not get double. 2 qubits will not be there.
Okay.
It is superposition state.
Yeah, that is in superposition.
That is the case. There you will get either 0 or 1. That's all, sir.
Okay, after measurement.
After measurement, either 0 or 1. That's all. Here you get 0 0 1 1. So it is this one. What you are seeing is super entangled state.
Right.
Only Hadamard gate means it is superposition state.
Okay.
Same result you will get. You can construct any circuit, sir, using here. This one you can construct. That's what I said. No, if you want to construct C not gate means here you should in the quantum circuit you should put three by three, because three inputs is going to be there, and CC not gate. So like that you can do it, sir.
Okay, sir. Okay. Thank you.
You can try it. If any doubt, you can ask me. I will do. We can for VTU two experiments. This is enough. You can
Fine,
show
sir.
it
Fine.
to students.
Sir, you can share your email address to the participants so that if they wanted to discuss with
Yes,
you,
sir.
let them.
Yes, sir. I will share it. So I will share it to you. You can share it, right?
Okay, okay, sir. I will.
The group. You have a group.
I don't have. I have to share through mail only.
Hello.
I have to share through mail only, sir. I don't have a group, sir.
Okay. Okay. Where is that to
Middle,
right?
sir. Middle. Stop sharing. Stop presenting then.
Okay, this one. No, this one.
Uh,
No, that is okay.
message. You can send
Message.
message
I'll,
to
I'll share the message here. Different platforms you're using. That's why I'm struggling. Where is the message, sir? Can you help me?
so in the participants list side, sir. Right side.
Participants list. We have to go. Correct, correct. Okay, okay. This is hiding. This one is hiding.
So if anybody having doubts, please
Yeah, yeah. Now I got it.
ask me, sir.
They.
I'll share the
Sir, I'm,
documents as well. Sir has shared one Bell State text document. I'll share with you all, and as well as one more PDF file is there. How to use the Qiskit. That is also I'm going to share it with them.
sir, I shared my mail ID.
Yes, sir. They are received, sir.
That one you can do it, and slowly they can play with this code. They are not familiar with the codes. Slowly they can play with the code, and errors will be there. So you can rectify the error by going through it. Otherwise, some AI platforms are there. There also you can get the help.
Okay.
Any doubts?
Sir, how to log into the IBM quantum computing, sir? Is it necessary to log in into?
Ma'am, for simulator, it is not required. Just as I shown you, you can just, sorry, I'll share my screen again. You can just type IBM quantum computer. You will get it, madam.
Using your Google account also you can log in, madam.
No, just see. Now my screen is visible, I think, right?
Yes, yes.
So I just open the window. Google is there. I just type IBM quantum experience. So IBM quantum experience. You just type. You'll get IBM quantum platform. So this is one where with no installation anything is required. You can just click and go to the composer, start building. You can use it. And if you want to sign in, you have to use a Google account, and so many things are there. You have to use that. You have to create ID, and then you can do it. In that, you can use more qubits. More than 4 qubits means you can. I have shown you one circuit. No, here one circuit is there, already built-in circuit. See, for example, quantum Fourier transform circuit. Where is it? I shown you one circuit is there. So that circuits you can, if it is more than 4 qubits, you can go for Qiskit, and you can run it. Is it clear, madam?
Yes. Thank you, sir.
Welcome, madam. So any other doubt? I don't know, sir. I didn't do recording. Sir has to check it.
Sir, I have a small query.
Yes, sir.
Actually, as you used the single qubit, then you have taken the control NOT gate.
Yes, sir.
And instead of that, can we take two qubit and then we take the control NOT gate? Anyway, both are two qubits only. Can we
Uh,
take and can we
which
get
one,
the
sir?
that last one which you show the code? There you
Hmm.
have taken,
Code. Okay.
yeah, in that
Hmm.
you have taken the Edamat gate
Hmm.
and then you
Hadamard
take,
gate.
yeah,
Yes, sir.
Edamat
Hmm.
gate, yes, Edamat gate, and then you taken the C naught.
Hmm.
That is instead of Edamat gate, can we take both two qubit, that is control NOT gate, and then we can get the two output of it.
So you are asking like this. Just a minute. So what is your query is? So I have taken like this. Yeah, Hadamard gate
Yes,
and yeah, C naught gate.
yes.
So this is qubit one. This is qubit two. So what is your question, sir?
In my questions, instead of Edamat gate, can
Hmm.
we take the two qubits?
So two qubits I'm taking, qubit
Yes.
one and qubit two. Then what I have to add, sir, here?
And suppose if you take the two qubits, if you consider, and again,
Hmm.
if the two qubits of control Z gate, if I take,
I have to use control Z gate.
yeah,
Okay, control Z. Then
okay. And in this case, I just need to get the output. That output has to obtained in the code.
that one you can do it, sir. It is C Z gate. CZ, that is enough. It will get, you cannot use control Z gate in single qubit. Whenever you use two qubit gate, you have to do two by two, because two qubits only we can use control Z gate.
Okay.
So in that code, how you can modify the code is, so you can have quantum circuit two by two, because you are going to use control qubit, correct?
Yes.
So control Z gate means it is two qubit gate.
Mm.
So here H naught is required, only CZ is enough. Here you can just put CZ. CZ means then you will get control qubit gate. So if you run this one, you will get that one. So I have to change little bit because Hadamard gate is there. So like that you can do it, sir. Did I answer your question?
Yes. Fine, sir.
If you want to use control NOT gate, that is Toffoli gate,
Okay.
you have to have three qubits. So for example, you need control NOT gate. So
Control. Okay.
control and NOT gate means, that's what I said, you have to three by three, because this first three represents three qubits, one, two, three. Okay. The second three, we are going to measure A, measure output B. This also we are going to measure, and C is control of AB.
Yeah.
A and B should be controlled. So when you write the truth table, you will write it as A, B, C as input. So this inputs you write A, B, C as input, and output, when you write the truth table, output you will measure this one. So A will be there, and B will be there, and the output. So what you are going to do is you are going to measure three outputs. So that is why three is there. You are giving three inputs. That is why this three is there. Whenever output means it is classical output. So that is why three. For example, in your circuit, you are not going to use this A and B. I don't want this A and B. I want only the third output, means you can write 2, comma 3, comma 1. So like that you can write. Only one bit you are going to measure. So like that you can change it in the code, sir, depending upon your uh, circuit.
Thank you.
Welcome, sir.